Network mounts can feel like magic the first time you see them, because files appear in the local Linux directory tree even though the storage is actually somewhere else, on another machine, across the network. The exam includes network mounts because they combine several Linux fundamentals you have already been building: mounting as a visibility layer, identifiers, and boot time timing, and the idea that not all failures are local. When storage is remote, you must think about two computers and the network between them, which changes what symptoms mean and how you interpret missing files or slow access. In Linux Plus questions, network mounts are often used to test your ability to separate a local file system problem from a connectivity, authentication, or protocol mismatch problem. You do not need to configure a network share during the exam, but you do need a reliable mental model of what NFS and SMB are, why they exist, and what kinds of symptoms appear when they are misbehaving. By the end of this episode, you should be able to describe the purpose of network mounts, compare the general roles of NFS and SMB/Samba, and recognize common symptom patterns that point you toward the right layer of the problem. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A network mount is the act of attaching a remote file system or shared directory into your local directory tree so programs can access it using normal file paths. From the viewpoint of an application, it may look like just another folder under a mount point, but behind the scenes, file operations are being translated into network requests to a server that owns the data. This translation is powerful because it allows centralized storage, shared access, and consistent file locations across many machines, which is common in environments with multiple users or multiple servers that need shared data. The exam cares because the moment storage becomes remote, the system's behavior depends on things that have nothing to do with the local disk, such as network availability, server responsiveness, name resolution, and permissions that might be enforced on the server side. That means a missing directory might not mean the file system is corrupted. It might mean the network mount did not happen, or the server is down, or the user is not authorized. Network mounts are therefore a perfect place for the exam to test discipline layer thinking. Is the path missing because the mount is missing? Is the mount missing because the network is missing? Or is the network fine, but the permissions deny access? If you stay calm and sort the symptom into the right category, the question becomes straightforward. It helps to think of network mounts as a client and server relationship, where the client machine is the one doing the mounting and the server machine is the one exporting the shared content. The client needs to know where the server is, how to speak the right protocol, and what identity to present if access control is required. The server must be running the sharing service, must export the correct directory, and must allow the client to access it under the correct rules. This means the success of a network mount depends on agreement. The client and server must agree on location, protocol, and permissions. When agreement breaks, symptoms appear, and the exam often describes those symptoms rather than telling you directly which piece failed. A strong learner listens for clues about whether the client can reach the server at all, whether the mount exists but feels slow, or whether the mount exists but access is denied. These are three very different states with different explanations, and recognizing them is what the test is measuring. You can solve many network mount questions by simply asking, did the mount happen? Can the client reach the server? And is the client allowed to access the share? NFS is a common protocol used for sharing files in Unix-like environments, and its name tells you what it is: Network File System, NFS. The core idea is that it is designed to let a client access files on a server in a way that feels native to Unix permissions and Unix-style paths. NFS is often used in environments where Linux and other Unix-like systems are the primary clients, such as server farms, research environments, and enterprise Linux setups where shared home directories or shared application data are needed. The exam's focus is not the version number or the deep mechanics, but the high-level idea that NFS fits naturally in Linux contexts and often maps well to Linux concepts like user and group identities. When a scenario describes Linux systems sharing directories with each other, NFS is a likely candidate because it aligns with that ecosystem. It also tends to appear in exam questions about centralized storage for multiple Linux machines, because it is a classic solution to that need. The key is to recognize NFS as the Linux-friendly network file sharing approach, especially in Linux-to-Linux sharing stories. SMB is another widely used file sharing protocol, and it is strongly associated with Windows environments, though Linux can both consume and provide SMB shares. On the first mention only, that protocol is Server Message Block, SMB, and when Linux provides SMB file sharing, it often does so through Samba, which is a suite of services that implements SMB-compatible sharing. In practical terms, SMB shows up when Linux needs to interoperate with Windows systems, or when an organization uses Windows-style file sharing across mixed operating systems. The exam includes this because many real environments are mixed, and Linux administrators must understand how Linux interacts with Windows-style shares even if the Linux machine is not the primary file server. When a scenario describes accessing a share hosted by a Windows server or integrating with Windows authentication concepts, SMB and Samba are likely to be involved. The important concept is that SMB is not a Linux-specific protocol. It is a cross-platform protocol with deep roots in Windows environments, and Linux uses Samba to participate. Recognizing this helps you infer which protocol family is relevant even when the question does not explicitly name it. Comparing NFS and SMB at an exam-friendly level is mainly about recognizing the environment and the identity model that feels most natural in the scenario. NFS tends to feel straightforward when Linux machines share with Linux machines, because the user and group model often aligns naturally, though details and security choices still matter. SMB tends to be the common bridge when Windows and Linux need to share files, because SMB is the language Windows uses for file sharing and Samba is the Linux side of that conversation. This does not mean you cannot use SMB in Linux-only contexts or NFS in mixed contexts, but the exam often points toward the most typical pairing to test whether you can read the environment correctly. Another difference is how clients experience access and authentication, because SMB often involves Windows-style share semantics and may involve different authentication workflows, while NFS often emphasizes Unix identity mapping. The exam might present a symptom where access works for one user but not another, or where permissions look different than expected, and the protocol choice can influence what is most likely. Your job is not to be an expert in every mapping detail. It is to recognize that identity and permissions can be handled differently depending on protocol, and that mismatches can explain confusing access behavior. In other words, protocol influences symptom interpretation. Now let's focus on what symptoms look like, because this is where network mount questions become predictable. One symptom category is a mount that is simply not present, meaning the path exists as a directory, but the remote file system is not attached, so the expected files are missing or the directory looks empty. This often happens when the mount did not occur at boot, failed during the session, or was never configured correctly, and it can look like data disappeared even though the data is safe on the server. Another symptom category is a mount that exists but is slow or hangs when accessed, which often points to connectivity problems, server load, network congestion, or a server that is reachable but not responding promptly. A third symptom category is a mount that exists but returns permission errors when you try to access it, which points toward authentication problems, identity mapping issues, or server-side access rules. The exam will often provide one or two hints that place the scenario into one of these categories, and your job is to choose the answer that matches the category. If you build the habit of classifying the symptom first, you avoid being distracted by details that do not matter. A missing mount symptom is especially common because it can be caused by many different upstream issues, including a configuration problem, a boot time timing issue, or a network availability issue. If the system tries to mount a network share before the network is ready, the mount attempt might fail, and the system might continue booting without that mount, leaving the mount point directory empty. This is a classic boot time surprise pattern. The system boots, the directory exists, but the expected files are not there. For exam thinking, you should recognize that the directory existing does not prove the mount exists, because the mount point directory could simply be a normal directory on a local file system. If an application expects data there and it is not mounted, the application may fail, which can look like an application problem when it is actually a mount problem. Another version of this symptom is that the mount exists in one session and is missing after reboot, which strongly suggests the mount was transient rather than persistent, or that the persistent configuration is failing. The exam may describe it as a system that works until restart, and your mounting mastery should immediately connect that to persistent mount configuration and network readiness. When you see missing files in a network mount scenario, think about whether the mount exists at all before you assume the files are gone. A slow or hanging mount symptom feels different, and learning to recognize that difference helps you choose the right answer quickly. When a local file system is full, you often see write failures or clear errors, but when a network mount is slow, you might see delays, timeouts, or programs appearing to freeze while they wait for the server response. This can happen even when the mount exists and the permissions are correct, because performance depends on network latency, bandwidth, server load, and the health of the server's storage. The exam might describe a system that becomes unresponsive when accessing a certain directory, and the clue is that the unresponsiveness is tied to that path, suggesting a remote dependency rather than a global CPU or memory issue. Another clue is that the same system might operate normally when working in local directories, which suggests the problem is not the whole machine, but the remote access pathway. In exam reasoning, slow network mount symptoms push you toward thinking about connectivity quality and server availability rather than about local disk corruption. You do not need to diagnose the exact network issue. You need to recognize that the symptom pattern matches remote I/O waiting. This is an example of using behavior to identify the layer, which is the core exam skill. Permission-denied symptoms are the third major category, and they often confuse beginners because the mount may appear to succeed, but access fails once you try to list directories or open files. This pattern indicates the client can reach the server and the mount mechanism is functioning at some level, but the server is enforcing access controls that do not allow the operation. In NFS contexts, this can involve user and group identity mapping, where the server decides whether the client's user identity is allowed to access the files. In SMB contexts, it can involve share-level permissions and authentication, where the client must present valid credentials and the server checks whether the user is allowed to access the share. The exam may describe a situation where one user can access the share while another cannot, or where access worked previously but now fails after a change. And those are strong clues that the issue is identity or permission related rather than connectivity. It is also common for a permission problem to appear after a server-side policy change, which can break clients without any changes on the client machine. The practical exam takeaway is that permission errors on a network mount are often server-side or identity mapping issues, not file system corruption. Your job is to match the symptom to the most likely layer of control. Because network mounts depend on boot time timing and external availability, the exam also tests stability, thinking about whether a mount should block boot or be treated as optional. If a mount is essential for the system's purpose, you might want the system to make a strong effort to mount it and to signal a serious problem if it cannot. If a mount is optional or external, you often want the system to boot even if the mount is unavailable, so the machine remains usable for troubleshooting and local tasks. This is a trade-off because treating a mount as optional can hide the problem until an application fails later, while treating it as required can prevent the system from reaching a usable state if the network is temporarily down. The exam often hints at which behavior is desired by describing the environment, such as whether the machine is a server that must provide access to shared data or a workstation that can still function without the share. The key is to align boot behavior with operational intent, which is the same contract thinking you learned with FSTAB. Network mounts make that contract more delicate because the dependency is outside the machine, so a cautious design often avoids making non-critical remote mounts hard requirements at boot. When you see a scenario about boot hanging or emergency mode triggered by a mount, think about whether the mount should have been treated differently based on criticality. It is also worth connecting network mounts back to the security trade-offs you learned with mount options, because remote storage is a trust boundary too. A network share might be managed by another team, might contain user-controlled content, or might be accessible by many machines, which increases the risk that malicious or accidental changes could spread. The mounting rules on the client can reduce risk, but the server's access policies are also part of the picture, especially for SMB environments where authentication is central. The exam does not require you to build a full security architecture, but it does expect you to recognize that network shares are shared for a reason and therefore require careful permission design. A scenario might mention that users should be able to read but not write, or that only certain groups should access a share, and the correct reasoning is that both client and server controls matter, with server controls usually being the authoritative source of truth. Another scenario might imply that a share should not be a place where arbitrary code runs, which connects back to execution restrictions and least privilege. When you interpret network mount scenarios, it helps to always ask who controls the data and what level of trust the client should assign to it. That mindset turns vague security questions into concrete decisions. By the end of this episode, you should be able to describe network mounts as the practice of attaching remote shared storage into the local Linux directory tree, making remote files accessible through normal paths while introducing dependencies on network, server health, and identity. You should understand NFS as a common Linux-friendly sharing approach, and SMB as the widely used Windows-style sharing protocol that Linux participates in through Samba, recognizing that environment clues often point toward which one is most likely in a scenario. You should also be able to classify symptoms into 3 practical categories: missing mounts that make directories look empty, slow or hanging mounts that suggest remote I/O waiting, and permission errors that point toward authentication or identity mapping issues. Most importantly, you now have a stable reasoning method for Linux plus questions. Confirm whether the mount exists, consider whether the network path and server are reachable, and then interpret access behavior through the lens of permissions and protocol expectations. If you keep that method steady, network mount questions stop feeling like networking trivia and start feeling like predictable consequences of a client-server storage relationship.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.